I'm Steve, and I'm really happy to be here today telling you a little bit about our work on building operating systems. Joint work, of course, with a bunch of grad students at Berkeley and also some really great undergrads who did a lot of the application evaluation we'll talk about later. So just to get this kicked off, I think one thing we should make clear right from the beginning is that when we talk about building operating systems, we're actually talking about this kind of building, the kind we're in right now, not any other sense of the word building. And I think that bears some explaining what I'm doing here talking to you about buildings at a computer systems conference. And so just to get us kicked off, I'm going to talk a little bit about our building at UC Berkeley, which is this Sucharjadai. It's a pretty standard building with a lot of standard instrumentation. But first of all, why buildings? You know, why is this an important problem to be tackling on? Specifically, why is this an important computer science problem to be tackling? Well, one reason is energy. So 73% of U.S. energy consumption and over 30% of electricity consumption and over 30% of primary energy consumption in the U.S. is actually consumed in buildings. And so this compares to about 3% in data centers. And so if we can make some small change to buildings that saves 5 or 10% of the energy and do it reliably, we can conceivably save more energy than is spent in all of data centers. Secondly, the second thing we learned when we started looking at buildings was that a lot of building occupants, people have a very personal relationship with their buildings, and yet, despite all this energy we're spending on them, they're not even very happy with it. Most people end up being dissatisfied. In fact, in a survey of building managers, the number one complaint is people are too hot, and the number two complaint is people are too cold. But okay, what does any of this have to do with computer science, right? And the answer is that there's a huge amount we could do about it if only we could program these buildings better. More than 70% of large buildings have digital controls. And digital controls, well, that sounds like a computer. That sounds really interesting. What sort of stuff could we control? And the answer is a ton. There's an enormous amount of sensing and actuation present in every commercial building, like this one, like the ones I'm sure you all work on. In our test building, there are literally hundreds of points of actuation just for the lighting system. There are hundreds of points for the air handling system. There's tens of electrical submeters, lots of temperature sensors. And so overall, there are actually more than 6,000 points of sensing, actuation, and control inherent in this building, all being actuated through the sort of really old-fashioned building management system. And so coming from the SensorNet world, like Rebecca mentioned, this is great. For years, we were trying to deploy networks with a few hundred nodes being a really big one, and yet all the time, right under our noses, there are these huge sensor networks right there, just waiting for us to do something interesting with them, and not only measure things, but also control things and interact with occupants on a really wide scale. So let's say we took control of these buildings, we had a better infrastructure for programming them. What sort of things could we do? Well, first, think about the kinds of applications you typically interact with, today in your buildings through your buildings. Well, if you have trouble coming up with any, that's probably pretty reasonable because you don't really interact with your buildings in any meaningful way. Maybe you have a thermostat in your office, although from being looking at a lot of building control systems, I can tell you this is usually disabled. So when you go up to the dial to say that you're too hot, it doesn't really do anything. Don't worry about it. It's fine. But what could we do if we were a little bit further forward-looking in the way we use these physical resources, which, like I mentioned, are computing a ton of energy. And they sort of break down in a couple of different categories. So one is this occupant thing. What could we do to give occupants new, surprising experiences using existing physical infrastructure? And how could we make those applications, the kind of things that pop up all the time at CHI and other HCI conferences, how could we make those really broadly deployable in a way that they aren't now, right? And how can we make them more than just demoware? There's also a huge energy aspect to this. Since they use so much energy, how can we just use better strategies to control how they use that energy? And in a large number of academic studies, they've shown anywhere from sort of 10 to 60% savings on various different types of loads in these buildings. And finally, how can we incorporate these into wider scale control loops to better manage the energy on the electric grid? We've seen a bunch of papers in the data center world about scheduling jobs across data centers so that we can, when the wind blows or the sun shines, we can use that energy better. Could we do that same thing in buildings? But since they use so much more energy, there's so much more potential. And so from a computer systems point of view, the goals and sort of challenges we had for this were, first of all, portability. So how do we take these applications, which are pretty much demoware today, and make them write once, run anywhere for buildings? Right now, the state of the industry is really poor in this regard. It's all a ton of hand-coded logic. And secondly, of course, now that we've started introducing these new applications, what are the new failure modes we've introduced, and how can we deal with them? Because these systems are fundamentally distributed. If you think about the physical extent of your building, the sensing and actuation is distributed across a large space, and so that sort of inherently leads to the same sort of questions you get in networked systems and dealing with transient and partial failures across parts of your network. And the current practice is that since they don't really have applications, their failure model is they just build you really nice hardware, and it's very expensive, and it generally doesn't fail that much. Is there a way we can introduce multiple processes? Like, can we run an optimization app alongside a personalized control application in these buildings, right? There's no concept of this in the current building because there's no concept of applications. And then finally, there's some nitty-gritty challenges we faced in actually making this real. How do we actually access the real physical building control systems and the existing hardware that's there and expose it out to the world and build all this other stuff we want to do on top of it, but in a way that's sort of principled, because the current systems are very stovepipe. You have one security system, you have one system for heating and ventilation, you have a system for lighting. And with all this, a key theme through all these is sort of scale. And this is scale in a bunch of regards. We want it to scale to a large number of sensors, we want it to scale to a large number of buildings, we want the applications to be portable at a wide scale. And we want them to be easy to write. And of course, you can't neglect security and privacy. And so the system we've developed in order to sort of try to accomplish all these goals, which sort of we built up from the bottom, but I'll present from the top down, is this BOSS, which is a set of distributed building operating system services that together allow you to write these applications or control processes which sit on top and portably interact with the physical sensors and actuators in your building to provide new services, whether it's the optimization service or the personal comfort service or the personalized microclimate service or the grid responsive electricity consumption service. These are all implemented essentially at a new application layer on top of a bunch of services. And within the set of BOSS services, it's designed to let us write those control processes in a way that is pretty much like we write processes now. The process can crash and the building will go on. And they're easily portable between platforms. So the first thing I'm going to talk about to achieve portability is this hardware abstraction layer. And so this sits in the middle of the stack between two layers. And so just to introduce sort of the challenge that this layer is solving, let me give you a quick overview. So the challenge is portability, and the problem is that buildings are custom designed. It's not like a computer system where you have a standard sort of memory hierarchy and a standard bus architecture, and everything is laid out in the same way in every building. The space to the use. And so let's say I wanted to implement a personalized microclimate app. So this would be an app that I put on my phone and it follows me around and adjusts the temperature wherever I am so that I'm more comfortable. We can argue about whether or not you'd actually want this, but it's certainly something you might want. And so what the app knows at the beginning is sort of where you are in the building, right? Maybe it has one of these fancy localization techniques, maybe you tell it where you are. In any case, it starts with knowing where you are in the floor plate. But this isn't really enough to implement this app, right? We need to map that information to different abstractions in order to actually be able to affect the temperature in that zone. Because the first thing I have to know is just where are the zones in the building, right? Because typically you can only control temperature in discrete regions within the building. And so I need to be able to go from a physical location to an actual part of the mechanical system that's provisioning the system for me. And then finally, once you do that, I need to map that into the controls view of the world, which tells me, how do I actuate in that zone? How do I actually control the temperature? And given the way these systems are typically designed, there'll be two things in that zone. There'll be a damper and a heating coil, and the damper controls how much air you get, and the coil controls how much that air is heated. And the setting of each of those will be exposed in the network in 2 points. And this is sort of state of the art in current systems for how you would find these points. The points have a name, which is sort of a hierarchical namespace, which encodes everything we know about those points. And so In this example, there are 2 points in the zone. There's a damper command and a valve command controlling those 2 things. And in that long string, sdh.mec, MEC, by the way, is sort of part of the network address of the point. It stands for Modular Equipment Controller. And then 4-21 is the actual zone name. It means it's on the 4th floor, and it's the 21st zone on that floor. And so encapsulated in this name is pretty much everything we know about those control points. And this is a really bad solution because it's totally unportable. This is just a convention in this particular building. The vendors try to enforce it, but it's totally unportable. And so what we really wanted anyway was to write the application in terms of the relationships. I wanted to write my application to say, change the temperature in the zone. I didn't want to have to go through some crazy regular expression mapping to figure out which points I wanted. And so what the hardware abstraction layer in BOSS is all about is modeling these relationships and providing an interface to the physical extent of the building and the layout of the systems in the building. And so what you have here is it's represented as a directed graph. And starting at the bottom, there's the spatial domain. So that's where we started in the example, essentially locating different objects in physical space. And so using that, we can map from the location where I am on the floor to a particular zone. But that also is overlaid with different views of the building, which overlap but are completely separate, right? Because another view of the building might be the duct network of the building, which has relationships involving how the air is blown through the physical building, which is, of course, also in the building, but doesn't really relate to the physical space all that much. But using the graph, we can trace backwards and find the particular zone controller that we're interested in for my particular space. And so now we're able to actually write the application in terms of a declarative language which specifies, for this application, map my current position to a VAV, and a zone. A VAV is the name for that box, which controls the amount of air. And don't worry too much about the syntax of that language. The point is that we need to be able to program applications in terms of the relationships between system components. So in that example, the system components were my spatial location and the heating and cooling system servicing that location. But we need to do this, in order for this to be portable and scalable, we need to not hard code this for each building. Because in existing buildings, what they do is you pay an installer to come in and set up and map all those points to the control logic, to the application UI, and that just gets very expensive very quickly because, I mean, there are 140 zones in that building. In this zone, every hotel room would be its own zone, and so it's completely insane to try to do this by hand. The next issue I'm going to address in any detail is sort of the reliability challenges that occur in this space. And so in order to know what sort of reliability problems you might have, we need to explain a little bit about how the controls are typically designed in these buildings. And this is a really typical control architecture looks like this. It's a 3-tiered system. So down at the bottom you have things like devices. And this would be like the damper or the temperature sensor in your room or any sort of analog to digital, anything that interfaces with the analog world. And these are plugged into controllers. Sometimes you'll see them as PLCs in the literature, programmable logic controllers, control programs. And these controllers are all actually on a network, or really what they're on is a bus. Two of the most popular protocols for that bus in this space are RS-45, the serial protocol, and ArcNet, which, if you've heard of it, was pretty much dead in the 80s. And so these controllers are all sort of on a network, and their interface to the outside world is provided through head-end nodes, which might provide an external interface via over Ethernet or IP or something like that. And since we're interested in existing, we wanted to use what was there and provide these new applications and new experiences on top of the existing control networks. But in this architecture, essentially what that means is all of your communication, whether it's your mobile personalized microclimate app or your optimization app, they all need to be talking down to these devices through this external interface. And in the existing system, that's really just for management. You can set schedules and things there. And so it's not really designed as a reliable component. And so failures of either the application or the connectivity to that system will have sort of long-lasting effects to the system. And so one thing we did in BOSS was introduce a transaction manager, which actually is a specialized hardware component that sits on the controller bus along with the other things and allows us to write applications against an interface which is designed to allow them to be fault tolerant. And so I'm putting transaction in quotes here for a few reasons. First of all, transactions is a way of reasoning about what happens, right? When you make concurrent updates to a system and providing some sort of snapshot, some sort of isolation requirement between different things. And that's sort of what we want here, but the problem is the same but different. So we are writing to distributed physical resources, right? Because these things are spread out through the building. You could have partial failures where some actions succeed and others fail. And so transactions for that is a good model. But also our actions are interacting in physical space. If I open the damper but fail to open the heating coil, I might get cold air instead of hot air. And so that could be an unacceptable failure. And so what we do in BOSS is we extend the idea of writing with some ideas from computer science. Essentially priorities, leases, and notifications, so that when an application writes in, they can be notified and choose whether or not their actions succeed or fail. And this has been a key primitive because now what this allows us to do is write those applications in an unreliable environment on EC2 or in our data center or whatever, submit their changes to this component which run, and know that if they fail after they submit them, they will eventually be reverted when their lease expires. So without going into really too much more detail about BOSS, this is really sort of just the tip of the iceberg when you get into starting to program commercial buildings, because they're just really complicated environments and there are a lot of interacting pieces. Some of the other pieces you'll see if you look through the paper are the hardware presentation layer, which has actually been a significant piece of work within our group. It turns out that the sensors and actuators in these buildings are all exposed over really archaic protocols, which are very insecure and also difficult to use. And so we've written about 30 drivers for a large number of building management systems and different hardware components to expose, about 30,000 data streams into BOSS from across campus. Which present a total rate of actually about 500 readings a second. So this is all scalar time series data that's going into a different service which is part of BOSS, which is providing applications access to historical data. And then on top of all that, we've built a family of applications which use all of these primitives that are inherent in the other parts to do analysis, to provide personal control, to do the personalized microenvironments and the optimization. And we've installed all this in quite a number of places. So it's fully installed in our test building, Sutar-Jadai, but we've also installed different pieces of it in like 4 or 5 different buildings across the world, really, including the New York Times building, a few other buildings on campus, and buildings at Lawrence Berkeley National Lab. And so it allows us to write very short portable applications, which are then portable across these different environments. So to sum up, I think that there's a lot of opportunity here, but also a lot of confusion, because these applying computer systems designed to these buildings, there are just a lot of moving pieces involved. There are, of course, the computer systems challenges dealing with the distributed failure cases, but you're also interacting with these legacy control systems, which are very brittle. And of course, buildings are actually inhabited by people who care about what you do, which in some cases limits what you can do. Nonetheless, we were able to achieve 30% electricity and steam savings and 60% lighting savings in sort of some portable test case examples, replicating some results from the literature and showing that there really is, that huge potential we started out with really is there. And we've open sourced a lot of this through this map project at map.cs.berkeley.edu. And so if you're interested in sort of the data plane of the system, that's all downloadable. But I think there's also a really interesting sort of future work agenda, both for us and for the broader community, at the interface of control systems and distributed systems and networking, because these systems really are fundamentally distributed. And so a lot of the work people do here about partial failure and observability and even constraint checking would be extremely applicable in this setting, I think. You see all the time these news reports about the latest SCADA system getting hacked, and when you go look at the design of these systems, it's because they're not designed to be connected to the internet. But what we need to redesign them so that they can be connected to the internet, and I don't think that's as simple as just applying sort of the best practices. You know, installing more firewalls or more hardware components just is fundamentally a losing battle. We need to take some of the techniques here and compile some of the constraints into the network so that they're really observable and make sure we can really verify that applications are behaving correctly. And some of this shows up in BOSS, but there's just a huge amount of work to do there because it's such a complicated field. So with that, thanks. I'm happy to take questions.
Hi, Naveen Duchen, MSR. Very interesting work. I'm curious, when you show all these multiple control systems, how do you provide good handles on coordination between them? For example, when you take your initial goal of saving energy while still making the environment comfortable, for example, is it better to run like a building-wide fan versus users turning on the AC in individual zones or rooms?
Yeah, so I think that really hits kind of the key is that there's a trade-off there in the way you deliver a lot of these services, and right now they're statically configured. And what's required to figure out how to do it best, essentially, is a level of modeling and observation that isn't really done right now. Right now, people just sort of statically configure them. And so what you would need to do in that case really is model, well, what's the trade-off here between the energy consumption of just conditioning all the zones versus allowing people to request their individual preferences and then make that trade-off dynamically, because it could change over time too.
So, and the second follow-up question is, so you show this history module, when the applications provide these controls, do you also expose the cost of making those changes, those decisions, so that this becomes much more transparent to them?
The energy cost or like the complexity or?
Both, I mean.
We don't really expose that actually. It's pretty much hidden inside of the transaction manager. That's kind of interesting idea though.
Thank you.
Thanks.
Hi, Curtis Heimerl, UC Berkeley. So I hope this wasn't actually the question. I was a little distracted thinking of it while the previous speaker was saying something. But as one of the few people I would guess here with an HEI hat, what's interesting to me here is having the users program their own environments in sort of a fundamental way. How far away are we from that?
I think it's really our goal actually is to allow people to interact with the stuff around them, and the key challenge there is really that mapping that I mentioned, is just finding the stuff. If you want to generate an interface for the things around you, you have to have some way to plug that all in and find out where it is and what you can do to it.
Well, it seems to me the key challenge is going to be mitigating differences of opinion when you have basically a large number of people trying to program competing environments, competing equipment.
Yeah, that's certainly the HCI challenge.
Yeah. Great. Thank you.
Gunsu at Cornell University. So this is a very exciting new domain. So having experienced a little bit of this kind of work at Cornell, my experience was that the ground truth is actually very difficult to obtain from the physical plant people. Have you thought about how you would discover whether or not the wires are indeed wired the way you think they are, or they're telling you they are?
Yeah, that's a great question. So in these systems, right, like you mentioned, a lot of the time they're either misconfigured or just plain wrong. And so one of the things we've been doing is sort of trying to work on some self-validating models. So I mentioned we created this metadata graph which relates all the components, but that actually also gives you sort of a toehold to start to validate that, because if you can actuate things, you can start to go in and poke things in different directions and try to verify, if I open the damper, does the thermostat respond? Does the airflow go on the upstream air handler increase? Is everything consistent with my model of the way it's put together? And so, yeah, I think that'll be really important, because one of the big problems is sort of the as-built problem that people say you get drawings or something and they're the way it was designed, but not the way it was put together. Another great topic. Thanks.